Log on, tune in, find out. Another good idea from Cambridge.
Our first speaker will be Sujit Sahu from the University of Southampton, and he's going to speak on Bayesian adaptive design for state space models with covariates.
Okay, thank you, Stephanie, and I would first of all like to thank the organizers for giving me a chance to speak here, and it's especially nice to come back here. My first job, first post-PhD job was in Cambridge, and at that time we were based in the Mill Lane. There was a warehouse. We were based in the warehouse in Mill Lane, and what I remember of that was there used to be lots of cows grazing around the river Cam. We always thought that's perhaps to compensate for the number of PhDs is in working around here, but that's 14-15 years ago. But it's nice to be back, and especially nice to be everybody from Southampton, including the chair. And in my talk today, I have collaborators Alex Dolia. He was a postdoc, he left, and then Sue, who is I think well known here, and Dave Woods as well. So it's especially nice to be present among them, because any hard questions I can just hand over to them, so they have something to say on this talk as well. Here is a brief outline of my talk. Partly I will give a motivating example why we are considering this design problem. I'll say something about these state space models, the flavor of the model that we are working with, and then we'll discuss a few points of this network design problem. We'll pose the problem and then develop some criteria, and then I'll illustrate with two examples, one simulated and one real life example, and then just end with some discussion. So I'll illustrate that whatever we are doing makes sense, and we do get a better design than what's available out there. So why state space models? Because spatial and spatiotemporal modeling is making quite a lot of advance in all sorts of areas, like in environmental modeling, healthcare, climate studies, and soil mixture modeling. Quite a lot of areas there, because increasingly data, we get GPS data wherever we get geocoded data, and those data seem to have a time difference as well. So that's why we need to consider state space models. And for example, like in air pollution, how shall we, the design problem is how shall we choose the locations, and this happens to be a map of the eastern US, if you haven't seen that already, and this is the existing network of ozone monitoring sites. There are about 700 ozone monitoring sites in there. So the problem could be, I work with people in the US EPA, they want to know, I want to remove 50 of these 50 stations, and I want to add 20 new stations. How shall I do it? What's the design problem? And they have 10 years, 15 years of data, loads of millions of data points that we have already. So that's sort of problem we want to solve, and I would just say that we just have got started, and we have some ideas. That's what I want to illustrate here. And here we shall consider ozone pollution, as I said already. So brief introduction about ozone. Why should we care about ozone? First of all, fact is ozone high up is good, and ozone down below is bad. So down below, this ground level ozone is a pollutant, and there are laws and standards and regulations to control ozone pollution. And this ground level ozone has many bad health effects, like it's especially for people with vulnerable people with respiratory illnesses, like people suffering from lung condition or asthma and so on. So this is well established, and I'm not going to go into any detail, well established scientifically, and I'm not going to go into details on that. And another fact about ozone is this meteorological conditions affect ozone production, like sunlight, high temperature. I will show that in the next slide, how ozone is formulated. At least that will be my attempt at explaining the chemistry behind. But These are important. These meteorological conditions are important in explaining ozone, and because of these meteorological conditions, the high ozone season is primarily in the summer, from May to September. That's summer in the US, not like in Australia, I guess. And ozone is a secondary pollutant. This is my equation. This is my equation or chemistry equation for ozone. Basically, sunlight plus volatile organic compounds, which are like organic gases, which are emanated from trees and other vegetation like these VOCs here, and plus nitrogen oxide. Nitrogen oxides are gases like from which are emitted from car and coal power plants. So these together, these bake together to give ozone, and ozone is O3 or 3 oxygen atoms, and that's how ozone is formulated in the air. So what one conclusion that we can take from here is that meteorological conditions affect ozone productions, and these should be included as covariates, as significant covariates. And there is also high temporal correlation because from day to day, so that we should take in modeling as well. That's why we need space-time model. That's why this state space models that we are considering. So this is a model that we follow up from one of our ozone modeling paper in JASA 2007. So at time t, we have observation factor ZT, which will be KT YT plus epsilon t. This YT is the n by 1 true underlying spatiotemporal process. So this is basically observation equal to truth plus error. So that's there in all sorts of in hierarchical modeling. And this KT is like the incidence matrix, binary incidence matrix. It identifies the locations where the observations are made, basically 1 or 0. KT will have element 1 or 0. And in this talk, we will take like this NT equal to n for all t. NT is how many observations we collect at time t, and n is the whole number of possible locations that we can ever make observations. And so in this talk, we will take NT equal to n, but the setup would allow to have different number of observation stations at every time t. And we will assume that epsilon t follows independent normal 0 sigma epsilon distribution. So in spatial statistics literature, this epsilon would be called the nugget effect, and the way, and so on. But we don't need to go into that much detail. So we said there will be some autocorrelation. So we'll assume this YT is HT YT minus 1, autoregressive process of order 1, plus we will assume that there is covariate effect xt beta, and plus eta t is a space-time intercept, which will have a spatial covariance matrix, and we'll assume that to be independent in time. This eta t to be independent in time and independent of epsilon t. And how this comes up, how we thought about that is YT minus HT YT minus 1. So that's like increment. That increment in ozone will be related to increment in weather, and because this weather is local, so this will be the local adjustment, and that's how we thought about the model, and that's how we can justify the model. And I told that this xt will be the meteorological effects, and that's a significant covariate, so that should be included in there. And rest of these are details. So basically we need y naught, like all the autoregressive process, we need initial conditions. We assumed parameter values and then did a sensitivity study of these a naught and a naught, and we assume a prior normal beta naught sigma beta for beta. So that's how our model is, and we'll assume that HT equal to HI. So that this is plain simple autoregressive model, as I alluded to earlier. This sigma epsilon is sigma square epsilon identity. So that's the nugget effect, or microscale variation, or it can be justified in terms of measurement error as well. And then spatial dependency we need a sigma eta. So that is a spatially colored covariance matrix, and sigma eta is a entry would be sigma square eta times. This is a correlation which depends on the distance between two sites, Si and Sj, and a decay parameter phi. You can have another smoothing parameter, but for simplicity we'll just assume exponential covariance structure here, and that is how we'll go. So, dij is the distance between locations I and j, and pi is a decay parameter. We will assume pi to be known, and then there will be sensitivity study with respect to pi and so on. So, I'll say more about the parameters little bit later. So, choice of rho and the effective range. The Materran covariance function will be chosen, can be chosen for rho, for the function rho, and we will illustrate with the exponential covariance functions, as you said, is rho d phi is e to the minus phi d. One concept important is what is this effective range. The effective range is the value of d for which essentially there is no correlation if two observations are taken at that distance apart. Now, if two observations are taken that distance apart, there is no correlation, effectively no correlation between those two observations. That distance d is called the effective range, and from here for exponential covariance function, in our case it is simply 3 over phi, because if you equate that to 0.05 and log 0.05 is approximately minus 3. So, that will be 3 over phi. That is how the effective range, that is how we will characterize spatial correlation. How, what is the effective range in which the correlation dies down, that is how we will characterize this. So, this is this is how the parameterization, our model parameterization would go. And now, we will talk about a problem network design. So, this is basically elaborating our setup, what all things we have like. So, our objective is to find methods for the dynamic at time t addition of m movable monitoring stations to an existing fixed network in the presence of covariates. I said the covariates are important, so the presence of covariates is there, and we would like to find out where we would like to put those m stations. And there is often a set of candidate locations where placement of a station is feasible. So, like for example, should avoid including location on a motorway. I mean, if you think of continuous design, it may land up in the 3-lane motorway. So, we must try to avoid that. Suppose we have a set of feasible locations where we can move to, and there are n candidate locations. So, this is the discretization of the region, and where we will be sampling n stations at particular times. So, basically n minus fixed stations, and we need to select m movable stations from n minus n plus m remaining candidate locations. So, at time t, we place the m movable stations at m locations chosen from these n minus n plus m candidates. And for large n and reasonable m, like 1000, capital N equal to about 1000 and small m about 20, this will be a hard problem, hard combinatorial problem. So, we basically we need to find and still we need to find an optimal design. So, what is the optimal choice of these m locations for each for each t? We may want to predict at an unobserved set of locations, or estimation of the model parameters that describe both the mean and covariance at time t. I have described the model, the covariance function, and the mean parameters as well. So, estimation of those model parameters, or we may want to predict, and depending on specific objectives that we adopt, we may consider two types of design criteria, like an entropy sort of criteria that focuses on prediction. Often this leads to prediction uncertainty, often this leads to the conditional variance. If you want to predict at a new location, what is the prediction at what is the conditional variance of that observation of that prediction, and or an information criterion, that is expected Fisher information matrix that arises from estimation of both the regression and covariance parameters. So, we may get these two types of design criteria, and here we focus on prediction, but that really is in our model, that really is estimation of y t. In capital Y t is a very large vector, and we have already taken that in our model. So, for us prediction and estimation would be the same thing. So, the predictive surface at time t is given by y t. That is what I was saying, y t is very large. We have wherever y t is the population of the spatiotemporal process where we which constitute our prediction. So this is in our discrete universe. The true spatiotemporal process is given by yt, and because the ultimate utility of our model lies in prediction, hence we aim to choose a design that minimizes the variance of yt given the observations zt, zt minus 1 and z1. So this is going dynamically, and at each time point t we want to minimize sort of the minimize is within quote unquote, because now this yt is a vector. So how can, that's why this yt is a vector and it will have a covariance matrix. So we will use properties like trace and determinant, as is very well known here, to find our design criteria, and for this dynamic problem we will adaptive Bayesian criteria. So the calculations should come out to be like this, like the conditional variance, this is the variance of yt given observations zt, z2, z1. This will come out to be at plus qt, rt, qt prime. This you can easily derive that through whatever Kalman filtering or some standard Bayes rule. There is nothing but Bayes rule in this formula there, that we can calculate the variance. And because of our model, the details would look like this. At is easy to see, and then because xt beta is there, that's why we'll have this qt is at bt inverse and xt plus ht qt minus 1. This at bt inverse, that's what is sometimes I think called is Kalman gain matrix or something like that. And then this rt, that's the variance of beta, that's the marginal variance of beta, and that can be seen like this as well. So this can be derived, and then as we said earlier, like this we can find the trace or determinant of this matrix Vt as our criteria. So the conditional variance Vt depends on the unknown so we will realize that this depends on unknown parameters like those sigma epsilon and sigma square eta and phi and all that. A full Bayesian way will be to integrate these a functional of this Vt like the trace or determinant with respect to the uncertainty distributions of these parameters. That will be that uncertainty distributions will be either the posterior or the prior, depending on what you are what you have. If you have data, it will be the posterior, and if you pretend that you don't have data, then it will be the prior distributions. So that according to whether data are available or not. So we'll assume that the parameters Vt are known and use the plug-in approach. That's to a true Bayesian is very disturbing, but I tried to convince myself that I can do that. So that's why many questions here, you see, that's very alarming, like why, how could you justify these plug-in? Plug-in values are typically obtained as estimates from previous studies. I said there are many years of ozone data and air pollution data you can just take. This approach sacrifices estimation of uncertainty for computational tractability. I mean, we can in our algorithm we can get an estimation step, but that will slow us down quite a lot. And formal statistical inference, assuming all parameters are known, will proceed after data collection. So, and in our study and examples, we did use whatever estimates that we had from our previous paper. So that's how I can justify. And we have performed sensitivity study to investigate the choices, and this avoids the need for prior specifics at the time of sampling, and that's an environmetrics paper that they also say that. So hopefully I won't be asked hard questions about that. So formally our design selection criteria would look like this, like at time t we'll find a design xi t star. It's xi t star, it will depend on time, and here will that design will be the argument of the minimization ut is it, where ut is a trace or something, and this will call the APV or average posterior variance, or we can call the average predictive variance as well. So I think we thought average posterior variance is a better term than in our setup at least than predictive variance. And to compare two designs, we can get this APV ratio, which is for design 1 and design 2. So this will be the optimized traced trace under design 1 and optimized trace under design 2. So, I think we are ready to go to one of the examples. So, this is a simulation study, very small simulation study that we started with to see what kind of results we can get. So, what we want to compare designs found for models with and without the spatially varying covariate, and our design looks like this. It's a, we take capital N equal to 49, that's 7 by 7 grid, and so the single covariate spatially varying, it takes the value 1 here, it takes the value -5 here, it takes the value 0 here. So, we just chose and wanted to illustrate what will be what sort of differences we get. We will take the temporal correlation to be 0.9 and an effective spatial range of about 4.3 units, and that 4.3 units you should, that's about roughly half of 8.5, which is the maximum distance between any two locations. So, designs in the absence of covariates, we can compare those designs with in the absence of covariates by Weichel and Royal in an environmetrics paper that can do. So, we take n equal to 5. So, at every time point we are sampling 5 locations, and with n minus 5 fixed stations and m movable stations, and that m will vary from 1 to 5, and we find an optimum design for each of the two models, like one with the covariate and one without the covariate, and we calculate the APV ratio under the model with covariate. So, that APV ratio greater than 1 favors the new design, and it's less than 1 favors the one without sorry. Okay, I'm about that. Thank you. So, you can see most of these APV ratios are bigger than 1, and with some extreme values, like some APV ratios are very high at times. What happens is this, the other design that takes an excursion, or it doesn't sample the locations well in the presence of covariates. We had a picture about that, but I think we are just summarizing the results. That's why. So, basically what's the message from here is that ignoring the covariate may lead to designs with higher average posterior variance for YT. And so, now we'll illustrate, just illustrate how this will look like in a practical example. So, we consider the state of Ohio as a study region, and we take like 86 candidate locations at t equal to 30 time points. That's roughly a month that t equal to 30 time points, and we have two covariates, like one temperature that changes in time and space, and that has been created to 86 locations, because we will need those xt values. So, that's there, and this temperature is the most significant covariate from our earlier study. That's why we take it, and we have population density that's spatially varying, but static, at least within the month or so. So, and we take like h equal to 0.9 and effective range of about 300 kilometer. This is about 60% of the maximum distance between any two locations in Ohio. The maximum distance is about 450 kilometer between two sites in Ohio that we consider, and we take 5 fixed, n equal to 5 stations at each time point, and n minus m of those are fixed, and m equal to 1 to 5 are movable. If we do that, then this is how the APV ratio comes out. So, basically, so if we do not move any stations, the APV stays very high, and if you move stations, and if you move one station, this is this purple line, and then green, I don't know if you can see it all, but then the red for moving 3 stations, and the blue for 4 stations, and the yellow for moving 5 stations. So, you see the over time, and so it settles down, you get much better APV decrease within the first few time points. After that, when it has seen the space a bit, it wants to settle down. That's what is happening. And so, basically APV decreases as the number of stations that can be moved increases over the first few time points. That's what I summarized. So, I think we'll come to, So, this is one illustration of how the design points are when we move 5 stations all at the same time. so day 1 it could look like this, and day 2 it could look like this. So what what I am trying to say here is this is sampling the space well and moving the stations, and by doing this we know that we can get the APV down to the smallest as we can. So this is just an illustration rather than any profound point. What would be alarming if the 5 stations were all concentrated on a region, or on if they got clustered, that would be probably a little bit alarming. That's what I wanted to say there. And so possibly last slide. We have developed a new set of criteria for the adaptive collection of space-time data in the presence of covariates. So that and we shown that including covariates we can make it better, and a dynamic model is adopted with both spatial and observational errors. This is not always seen, like either the observational error is set to 0 or something in many papers, but we have illustrated that data may be collected more efficiently if covariance are taken into account. That's what we set out to do here for this practical ozone modeling problem. And this one good point of the criteria are analytically tractable, and so we do not require intensive computational methods to find the design. That's and this is very important, because the next set of problems that we want to go on to is like our current work is investigating the computational challenges of very large networks. Like you have 1000 by 1000 monitoring stations, so whatever spatially you want to do, you have to invert and multiply 1000 by 1000 matrices. That would be very difficult, and that we are doing in terms of modeling with some predictive process approximation. But I think we would like to put our hands on that sort of problems here as well. But hopefully that will be in time to come. So I would like to stop here. Thanks.
Are there any questions for Sujit?
Yeah.
Yes.
I have a question, but more philosophical, and this is good, but not just for you. Generally, if you do optimal design for smaller problem, you do the good mathematics, it's for the fun of it or for the mathematical beauty, that's one thing. But when you do optimal design for a very large problem, here's one thing. Are there case study to show that if the practitioner experimenter didn't use this design, use another design, would it make any difference or missing anything very big? And the difference I want to make as a contrast, you go back to classical work. The reason factorial was readily accepted is because if you choose one resolution or non-resolution, then the estimability become a problem. So the difference is immediate and seen.
Yeah.
So this is a very general remark for the optimal design community.
Yeah, I think very important questions. I think the answer to the first question is this plot. I mean, again, this is very small, but that we can improve when we have include covariates. That's this plot. Most of the points being more than one, so we do gain from the new design. So that's. I take your question like whether this will be true for a bigger problem. Of course, we haven't tried that, and we can expect to have that. And to answer the second question, like I mean, we can do this. Tractable designs would still be preferable in the second question, because the computation is very hard. And
I agree with you.
Yeah.
If you ignore a covariate or not ignore a covariate,
Yeah.
obviously the difference will be very big.
Yeah.
But my comment is more when, if two people, for example,
Yeah.
if I'm an experimenter, I don't know your work. I simply go to SAS and run something, including covariate.
Yeah.
And then you do very elaborate mathematical work, you may be 5% efficient. As an experimenter, do I appreciate or do I want to go through a complicated thing, or I just want to, I already pay for the software, I just do it. So this is a general question about the impact of optimal design in practice.
That's for every statistical method. I mean, you are asking a very general question. I do appreciate that. But if we see possibility of improving results, then obviously the new method will be better. And to answer like your second question, like whether estimability at high resolution or lower resolution, this is in our case, this is the finest resolution. We are modeling at point level. We are not modeling at area level. Like we are not modeling postcodes or districts or something. Ours is the finest resolution that you can. We have discretized it for this problem, for this design setup. We have discretized it, but I think we can, we can remove that discretization later if we want to. So in our case, we are modeling at the highest resolution, so we do not have any problem in estimation and so on. Okay.
Okay, we need to move on.
Yeah.
So let's thanks Sujit again.